Okay, so it's a great pleasure to introduce Pei-Chun Su from Duke University. Pei-Chun is currently a fifth-year graduate student working with Hao-Tiang Wu. He's on the job market this year. And prior to his time at Duke, he received his bachelor's and medical doctorate from National Taiwan University. And then a master's degree in bioengineering.
Yes. UCLA.
At UCLA, excuse me. And now he's at Duke, and now he's here. We're very happy to have him. So take it away, Pei-Chun. Thank you.
Hi, everyone, and thank you for Professor Wendy to invite me to have this talk. So my name is Pei-Chun Su. Today I'll talk about the optimal shrinkage of singular values under the noise structure with separable, covariance, and it's a comparison to the fetal ECG analysis. It's just a short introduction of my background. I was a medical doctor from National Taiwan University. So I'm interested in biomedical signal analysis. And right now I'm in Duke University doing PhD in mathematics. So today's outline, we will talk about what's the motivation of today's work. Then we'll talk about the background of the random matrix theory and what's the optimal shrinkage. Then we'll give the assumption and the theoretical result of my current work. Then we will apply our result and our algorithm to do a simulation and to have a real simulation on the real data. So let's start with the motivation. So what is a fetal ECG? ECG means the electrocardiogram. And the fetal ECG means that we want the detection of the fetal's ECG, the electrocardiogram of the fetus in mother's abdomen when we have the pregnancy. And why do we need to study the fetal electrocardiogram? Because there's a disease called the fetal cardiac arrhythmia, which will happen to 2% of the pregnancy, including the supraventricular tachycardia and the ventricular tachycardia and the atrioventricular block. Is some signal blocking and some abnormal signal in like the atrium and in the ventricular of the fetal's heart. And this kind of arrhythmia sometimes they will result in fetal heart failure and the demise of the fetus. So we need a tool to have an early detection and a treatment for the fetal cardiac arrhythmia and other kind of heart problems. So there are some existing detection methods, including the fetal magnetocardiography, that we directly put this huge machine on mother's abdomen and detect the heart signal through detecting the magnetic field transmit from the fetus heart through this kind of big machine and record the ECG. Also, we have another tool called scalp that we directly through the mother's vagina and put the electrode on the fetus head. So we can record the signal from the fetus directly through the electrode. Also, most commonly see we can use the fetal echocardiography that we directly apply the ultrasound on mother's abdomen to see the movement of the fetus heart. But these all existing detection methods, they have their own problem. Like for this one, the machine is too big and it's too expensive for to apply on most every pregnant woman. Every mother have a pregnancy, and this scalp technique, you need to put the electrode. This is a very invasive procedure. You need to put the electrode through the vagina and put on the fetus head. Which sometimes they will cause like an infection problem and some other complications. And for a fetal echocardiography, we use the ultrasound, but this one because we are using the ultrasound, so we cannot detect the electrophysiology of the fetal's heart. So and the electrophysiology is mostly important for a clinical doctor to detect the disease of the fetus. So these three machines, they have their own problem. So today I will talk about using the trans-abdominal maternal ECG that we directly put this electro few channel like a V1, V2, V3, V4 few electrode on mother's abdomen and collect the electro signal from the fetus. And this kind of machine, they are pretty small and they are not invasive. So you can if we can invent a more like a convenient machine, then like a pregnant woman, pregnant mother, they can just bring this kind of portable tools and bring it home, have a long-term recording of the signal, of the heart signal. But this machine, it also has its own problem that when we detect the electrophysiology signal, because we also have the mother's heart around here. And so there are two components. One is from the mother's heart, and the other one is from the baby's heart. So in one channel of the signal, you can see there's a big amplitude, which is from the mother's heart. And this small amplitude, they are from the heartbeat of the fetus. So today's problem is how do we decompose these two signals that we have only one channel or only few channels available, and how do we separate the mother's part and the fetus part? And also the other problem is that because there are a lot of background noise, like the baby can have the movement, the mother can have a movement, and we have some a lot of background noise resulting from the environment. So usually because of the fetus signal, they are very small, they have a small amplitude, and they have therefore our signal has a low signal to noise ratio. So how do we separate, how do we do to decompose a clear fetal ECG data for the clinical doctor to have a clear view of the data of the ECG of the fetus to have a better diagnosis, early diagnosis, and for early treatment. So the idea is that we can use the matrix denoise method. Like this is the signal from the abdominal ECG, and we have a lot of existing algorithms that can easily detect the huge peaks around for a mother's part. So if we have a very correct location of the mother's heartbeat, then we can, for example, we can crop each heart cycle of the mothers and align them together to form a big matrix. And the N is the number of the rows of the matrix, and the P is the number of columns. Then we want to apply a matrix denoising method to have a low rank of the matrix, to have a recovery of the matrix, which the matrix is only containing the mother's heartbeat cycle. Like for example, in this matrix, you can see after the matrix denoising approach, we only have the mother's signal here. And we want to recover this kind of low rank matrix construction, because this is a low rank because every bit, they look very similarly locally. And if we try to draw a P principal component and analysis of the heart cycles, then locally, this is true data, and locally we can see this kind of data is low rank. That means the number of eigenvalue, number of singular value in this matrix, they are very low. So if we can have an ideal matrix denoising method, then we subtract this low rank matrix with the original data. Then we will have only the fetus part remaining in this matrix. Then we can concatenate each row together. Then we can get the mother's part only and the fetal's part only. So the strategy to do the matrix denoising, we can in previous work of my advisor, they apply to take the median of the matrix. But the problem is if you only take the median, then each row they will be the same, which is not good for a clinical study, because the morphology, the shape of the heartbeat, they have the clinical meanings. For example, this small amplitude around before the huge peak, like here, they are called P wave. And this amplitude after the huge peak, they are called T wave. The height and the interval between each peak, they have the clinical meanings for the clinical diagnosis. So we want to, for every bit, we want to recover every bit's morphology. So if we use the previous method with the median, it's not ideally. So we will apply a method. It's called optimal shrinkage for the singular values. And so I will explain what is the optimal shrinkage later. So let's give a notation of our theoretical result first. This is the original matrix we get from the data, which is delta S, which contain the low rank signal, which we denoted as S. And the noise, we claim that this part is a noise, which contain the background noise like this, and the fetal signals around here. And we call the noisy data delta S, and then the noise code is Z. So the delta S is equivalent to the S signal plus the noise Z. And you can see this kind of the noisy matrix, they have its own structure, like the fetal's part, the fetal's ECG heartbeat location, they might be dependent with each other. Also, the variance upon each column, there might be a different variance upon each column. So there's a structure we want to have a more complicated structure compared to just like a background noise, white noise. And actually, if we draw the covariance structure, we can see as P and N, they go to the dimension of the matrix go to infinity. The covariance structure is not identity. So the noise matrix, it has its own structure, which is not a simple structure. So I will review some background of the random matrix theory and the optimal shrinkage. So the previous result in like Bana and George's paper and Nadakudi's paper in 2011, that they assume that when the dimension P is grow with N and P N divided by N, when both go to infinity, it converge to a value beta, where beta is between 0 and 1. And Z is our noisy only matrix, which is P by N random matrix. And this pi, Z transpose, this means the empirical distribution of the eigenvalues of the Z transpose. And it will converge in distribution to a distribution called rho 1C X, where rho 1C, they assume that it has a compact support. And similarly, we have this notation for the empirical distribution of the Z transpose Z, and the empirical distribution, it will converge to rho 2C, which also has a compact support. And we denote the Stiegler transform respectively with respect to the rho 1C and the rho 2C, and the N1C is simply the Stiegler transform of rho 1C, and the N2C is a Stiegler transform of rho 2C. And this is called it's called the D transform, which is just simply the Z times the N1C, N2C. And then here Z, we means that the Z is in the positive complex plane. For example, this kind of matrix, if we have Z is a simple white noise, that it has IID entries and the 0 mean and the variance 1 over N, then the empirical distribution of pi ZZ transpose, it will converge to a very famous law called Marchanko posterior distribution, where rho 1C X equal to this kind of deterministic form. The function is merely depending on the beta, which is merely P divided by N. And also the rightmost edge, where we denote T as the lambda plus. This is rho 1C, and the rightmost edge of rho 1C on the distribution, we call it lambda plus. And the leftmost edge, like in this case, is 0. We call it lambda minus. So, and when we have the beta equals to like a P equals to N, then beta will equals to 1. So for example, this distribution is for beta equals to 1. So the lambda plus here, it is equal to, when when you replace beta with 1, it equals to 4 right here. And then the lambda minus equals to 0 right here. So, and so the Marchanko posterior rule is only dependent on the matrix dimension, which is converged to beta. It has a deterministic distribution. But that is for white noise. But what if we have a more complex distribution? For example, this is a more complex distribution that is certainly not the Marchanko posterior rule. So today we want to generalize this model to a more complicated noise distribution. And again, we have a notation here. This is the empirical distribution of Z transpose. And we denote the eigenvalue of Z transpose as lambda 1 to lambda p wedge n. And when we have the noise matrix Z and we plus the signal, where the signal we assume this is a spike model when it has a low rank R and with a singular value Di, left singular vector, right singular vectors. And the tilde S is the signal plus the noise. There's a very famous law called the BBP phase transition. This is a very famous phenomenon that's derived by Bike, Ben, and Pei-Chun in 2004, which they apply. The matrix they study is not the same matrix, but this phenomenon is the same. That if we add the signal to the noise random matrix structure, then you can see there are some singular values pop out right here. And this is the others are very similar to the original distribution of the noisy only matrix. And here the annotation of tilde lambda 1 to tilde lambda p is merely the eigenvalues of tilde S and the tilde S transpose. So this behavior that the pop out singular values, they are called the BPP phase transitions, which means that when your signal Di is bigger than some threshold, that is alpha, then almost surely the singular value, the eigenvalues will almost surely converge to some theta Di, where theta is the inverse of the D transform, which has a deterministic decided by the T transform. But if your signal is too small, that's smaller than the threshold alpha, then you will converge to the rightmost edge, lambda plus. So the strong signal you will pop out here, but the weak signal, it will just almost surely converge to the rightmost edge of the lambda plus. And if you take a look of the eigen singular vectors, the left singular vectors, the original singular vector, which is mu1 here, and the biased singular vector is a tilde Cauchy1. It has an angle between them. It's not original direction of the original singular vectors. It has a biased direction. And the inner product of these two vectors will almost surely converge to some value determined by the spatial transform and the derivative of the D transform. And similarly, when the signal is strong, it has a value. It will converge to a value A1 Di when I is not equal to Z. But when if the eigenvalue Ij are different, then it will only converge to 0. And when the signal is too weak, then it doesn't matter which I or which J it is. It will almost surely converge to 0. So this is the old result from the Binai, George, and Nalakutis in 2011, the almost surely result. So what is the optimal shrinkage? Remember that our singular value D1, like Di, they will be biased to Y1, and the singular vector, they will be biased to another direction. So we want to reconstruct an estimator to recover the biased singular value, the biased matrix to the original matrix S. So we want to have a estimator of the original signal matrix S. So in like the optimal shrinkage, the idea is has already mentioned before, like in Nadakutic paper in 2013, and Matan Gavish and David Donahoe in 2013 and 2017. That they apply a nonlinear function on the singular values, and such that this is the original error if you don't do anything about the singular values. Then if you apply some nonlinear function on a singular value to shrinkage to another value, under some loss function, which is denoted as a Ln, then we want to minimize this kind of error. We want to reduce the original error to a lower error with respect to the loss function. And if the loss function has a asymptotic convergence, then the optimal shrinker is denoted as the shrinker which can minimize this loss, which is decided by the D and the X, which is the original singular values of the original matrix. But this kind of estimator, they need some information that how do we know what is the optimal shrinker, and what is the, because we don't have any information of the original rank of the matrix. So how do we have an estimation of the rank R here? So in 2013, the optimal shrinkage is already has an idea for any kind of general noise, that if this original algorithm for optimal shrinkage, that if you have the signal noisy matrix tilde S, then if you have an estimator of the rank, then you can compute tilde S as a singular value decomposition, and then construct the estimator of the optimal shrinkage. So, but the problem is that this rank is unknown, and although we have the estimate, we can have a closed form with the optimal shrinker, which is merely decided by the original signal strength and the A1 and A2, the inner product of the left singular vector and the right singular vector. And this form is decided by the Frobenius norm. And we also they also have the result for the operator norm and the nucleus norm in Matan and David Donahoe's their paper. But how do we do the estimation of this signal strength and this inner product? So Nadakuti they introduced a method that this is the biased singular value distribution. Then they take the first head R eigenvalues out, then they have a distribution like this. So they claim that this distribution is very similar to the original singular eigenvalue distribution of the noisy only data matrix. So they construct this kind of distribution, which is called the truncated distribution. Then they use this distribution to discretize the estimator of the signal strength and the inner product and the inner product. Because if you remember that these all values can be decided by the digital transform and the T transform, which is calculated by the integral of the empirical of the rho 1c and rho 2c, which is the noisy only data distribution of the eigenvalues. So we can use the truncated version of the eigenvalue distribution to have an estimator of the optimal shrinkers. But how do we know how many singular value, how many eigenvalues here we want to take out? So the problem is we don't have an estimator of the rank. And for the white noise situation, when the noisy matrix has zero mean versus 1/n and the finite force moment, then remember we have under such a situation, remember we have the Marchanko positive distribution, so we can merely decide it by the beta. So as the optimal shrinker and the bulk H can be determined by the beta value. So under white noise, everything is deterministic. So you can have a deterministic calculation of the optimal shrinker, and the rank can be just determined by how many eigenvalues of the biased matrix is bigger than the bulk H, and how many is smaller than the bulk H. The rank can be decided by directly computation, and this optimal shrinker can be directly computed. But in our case, the noise matrix is not white. So how do we, if we have a more general noise data, how do we perform the optimal shrinkage? So this is our most result, the most normal result of my research. So let's talk about the assumption and the theoretical result. Again, this is a SPI model that the signal has a low rank structure, and this is a singular value and the singular vectors. And we assume that the noise has a color and a dependent noise structure. That now Z is not merely the white noise, that it has it's equals to A square root times X times B square root, where X is just a P by N random matrix. You can say it has previously it has a white noise structure, or you can say it has a more restriction more generally. And the A and B, they describe the colorness and the dependence in here. And again, P and N, P grow with N, and P divided by N converge to the number beta. And here is the assumption for the noisy data, like A, X, B, that X has ID entries, 0 mean and 1 variance 1 over N, and the finite force moment. Actually, it should be finite 4 plus epsilon for some small epsilon moment. And the assumption of A and B, it has a singular value decomposition like this, eigenvalue decomposition. And these two assumptions, they are making sure that the resulting eigenvalue distribution of the noisy only data matrix, it has a compact support, and it's not all concentrated at 0. So it's just giving some regularity to the noisy only distribution for rho 1C. And we also have the assumption, more general assumption for the signal only matrix S, which it has a signal D1 to DR. And this is the threshold, which is determined by the D transform. And we give a notation of R plus, where R plus, that D1 to DR plus, they are a way larger than the threshold alpha. But for D with a value bigger than N minus 1 over 3. And for DR plus 1 to DR, they are around this range. They might be very close to the alpha, or they might be very away from alpha, which is smaller. So this is our assumption for the whole S and the Z. Then we have the result that when this is a BBP phase transition, when we have a signal plus a noise, then we study the behavior of the eigenvalue of delta S. That again, the signal here, when the signal is strong enough, like D1 to DR plus, then the eigenvalue of the delta lambda I will converge to theta, which we already know. But previous world, they only have the almost surely convergence. Now we provide a convergence rate, which this converges to N minus 1 over 2 with high possibility, which is described by this epsilon. So the first R plus singular value, they will converge, pop out like around here. And for the R plus to R plus plus 1 to R singular values, they will just converge to the rightmost bulk edge, lambda plus, they will be around here with this convergence speed. And for the remaining part of the singular eigenvalues, they will be exactly very close to the original eigenvalues of ZZ transpose, like tilde lambda R plus I, it will be very close to lambda I with this convergence speed. Besides, we have the behavior of the asymptotic distribution of the eigenvalues, that when this is rho 1c, and around the bulk edge, it has a square root behavior of the density of the rho 1c eigenvalue distribution, which has a square root behavior with the arrow term of x, order x. And similarly, we also have the result for the singular vectors with this convergence speed, that the left inner product will converge to A1 di, and the right inner product will converge to A2 with the n-1/2 convergence rate. And when the signal is too weak for R plus 1 to some more larger I, it will just the inner product will just converge to 0 with n-1/2 convergence rate. So let's talk about how to prove the singular value problem and how to prove this result, like for a singular value and singular vectors. That we it's a very traditional. This method is already used before, and we just write again for our model. That this D is constructed by the signal, the diagonal of D1 to DR. This is D constructed by the signal eigenvalue, singular values. And the U is constructed by the left singular vector and the right singular vectors. Then we construct H by the noisy only data matrix and the tilde H, which is constructed by the tilde S. Then you can see like tilde H is merely this H plus AU times D times U transpose. And this is a resolvent, the G of H, and this is a resolvent tilde G of tilde H. And the pi is constructed by the stereo transform N1C and the N2C. So the previous result by Naus and in 2013, we know that when we study the eigenvalue of tilde H, at the same time, we can study the eigenvalue of tilde S, singular value of tilde S. So if the eigenvalue, if mu is an eigenvalue in the spectrum of tilde H, then the determinant of this matrix should be equal to 0. So this is the way we decide the location of the eigenvalues, and we apply a famous rule called an isotropy local law that derived by Naus and in June in 2016 for a more simple data matrix. And this is an isotropy local law. So we can decompose this resolvent and plus the D to this pi plus D and the term here. So we calculate the determinant of the left-hand side and the right-hand side. Then we can have a determinant with this order, which is determinant by the anisotropy local law. So the eigenvalue should be making this determinant equal to 0. So we apply this idea and this property to decide the location of the eigenvalue and its convergence rate by the anisotropy local law. And the same idea can be used to prove the idea of the singular vector, the inner product, that we can write the resolvent tilde G to this using a scarce decomposition to write in this form. So you can see in this decomposition, it only has a component decided by the left singular vector, and the biased right single vector. So if U times the U transpose times U, then somehow you can see the inner product of the U of the original singular vector with the biased singular vector. So for example, here we want to study the left singular vector inner product. So it can be written as the integral of the D inverse and plus the UTGU here. And again, we can decompose this matrix into the pi and some value determined by the anisotropy local law. And we control these identities to give a convergence rate by the anisotropy local law and use the determinant here as 0, here the integral here, to give the almost surely convergence result for A1 and A2. Yeah, this is the detail of the proof is more complicated and bulky, so I just show you the idea here. Okay, so we have the convergence rate of the eigenvalue and the eigenvector, and we also know that around the bulk H, the rho 1c has a square root behavior. So we have this property, so we can apply this property to give a estimation of the optimal shrinker and decide the bulk H. For example, we know rho 1c has a square root behavior. So we from tilde lambda L, and we from the eigenvalue sticking, we know the behavior of eigenvalue here should be very similar to a noisy only single values. So because we have the density rho 1c, and we know if the lambda L to lambda plus, which is equal to lambda 1, it should be have L minus 1 eigenvalues around here. So this integral should be equals to equivalent, approximately equivalent to L minus 1 divided by P. And because of the square root behavior, and the square root integral is equal to the behavior of 3 divided by 2 with some constant. So we have the property, the distance between lambda plus and the tilde lambda L be approximate by this L minus 1 divided by P. So if we give another value, like another L, say like L prime, then we have another similar equation, which with the same constant C double prime. So we can apply this idea to give an estimator of the lambda plus the bulk H. For example, here I use the first L, I use the NC. NC, C is equal to some small number from 0 to 1/2. And the other value, I apply the lambda to 2 times NC. So I have 2 values, then I can have an estimator of the bulk H, which is called het lambda plus. Then when I have the estimator of bulk H, the rank can be simply estimated by how many eigenvalues are bigger than the bulk H. And remember our assumption that we assume D1 to DR plus, they are away from the threshold with the order of n minus 1/3. So if we want to recover these signals, the rank of R plus, it corresponding to a het lambda plus the n minus 1/3 here. So this is our estimation of the het of the R plus. And similarly, besides of the bulk H, we can remember that our result also show that the other for 1 to R plus, the eigenvalue will pop out. But for other eigenvalues, they will be around the bulk H. They will be very close to lambda plus. So how do we know, like here in this area, is it very close to the original distribution or not? So we just simply cut a lot of eigenvalue here. Say we cut K eigenvalues, and then we estimate with the same approach. We insert other eigenvalues, and we say it's het lambda J to here. So the idea is that we can reconstruct the original noisy eigenvalue distribution by this method, which is called imputation. the original idea is again motivated by Gavish and Donahoe, their paper about hard stretching hole method in 2021. So we use this kind of method to replace the top singular eigenvalues with our estimator with height lambda plus and the height lambda z to recover, to say this distribution is very close to the original distribution of a noisy only data matrix. So with this distribution, then we can have the estimator of the optimal shrinker using this eigenvalue, using this distribution for discretization. For example, in Frobenius norm, we have di, and for operator norm we have head di, also in nuclear norm. Yeah, I know. I remember I already changed the slide here, but I don't know why it's overaging. Yeah, I changed to your because the operator norm in the previous paper is wrong, and by Professor William we have another correctly estimator of the operator norm optimal for the optimal shrinker. It should be di times the square root of the a1 times a1 wedge a2 and divided by a1 v a2. Yes, the minimum over the max. Yeah, so it's here it's different. Yeah, but the idea is that we have the discretization of the optimal shrinker using this corrected imputation method of the distributions. So this is our whole algorithm, that we only have the input of the noisy only data matrix and a constant c, which is 0 to 1/2. Then we compute the height lambda, the bulk h, and the estimated rank. Then we compute the estimated distribution. Then we give the estimated optimal shrinker. So you can see in this algorithm, we don't need any other information. We just need the noisy data and some random, some decided by the user, some constant in 0 to 1/2. So we call our method, our algorithm is totally data driven. We don't need any information from any knowledge of the original signal or the structure of the noise. And we also, because of the convergence rate we proved before, then we can have the convergence rate of the how fast it converges to our estimator of bulk H. It converges to lambda plus, which the convergence rate apparently is determined by the constant C here. So we can select the C, which has a good convergence rate. Also, with high possibility, this event that our estimation of R plus equals to R plus. This event is an event with high probability. Also, we also have the convergence rate of the estimator of the shrinkers with this convergence rate. So we apply our algorithm to some simulations. For example, I can ask this, For example, we create two types of noise, that type 1 noise and type 2 noise. Type 1 noise is simply the white noise that remember our matrix, our noisy only matrix is A times X times B square root. So the eigenvalue of dA of A and B, they are just identity. So it's simply type 1 noise is simply white noise. And for type 2 noise, we give it a structure more complicated, that the eigenvalue has this kind of structure, and the eigenvalue of B have this kind of structure. Also, the signal, we also make it more complicated, like we make it has a rank 12, and it can be equal, like D1 to D3 equal to 4, like D1 to D6, D4 to D6 equals to 2.2. This, and because we have some knowledge about, because it's a simulation, we have some knowledge about the bulk H of this matrix. So we know that D1 to D4, they should be the rank, the R plus should be equal to 6 in type 2 noise. And this D7 to D12, they are small signals. They should be below the bulk H or around the bulk H. So we try to simulate and see how is our estimator of the bulk age is correctly estimated. So you can see for type 1 noise, when P divided by N equal to 0.5 and P divided by N equals to 1. You can see our method, which is the black line here. Our method has a very good estimation of the bulk age. And the purple line, the magenta line, is using the optimal shrinkage for the white noise in 2017 paper. So because it's white noise, we know that it already has a closed form merely depending by beta. So it also has a very good estimation of the bulk age. And the green line using a screenshot published by maternal and denoising in 2012-21. That they using like a hard threshold method to decide which singular values they should be remained and which singular value they should be cut off. But like this hard thresholding, sometimes even in white noise, they will cut off some singular values like here, that they will rule out some singular values which has the important information is away from the bulk age. So this is showing our result, the convergence rate. Also for a type 2 noise, it's a color and dependent noise. Apparently our method, which is a black line, has a very correct estimation of the bulk age. You see this black line is just at the rightmost edge of a noisy only distribution. And the second row is just the convergence, the error ratio of the original bulk age and our estimator. You can see as N grows, the error rate will decrease, no matter it's type 1 noise or it's type 2 noise. And because we have a correct, we know what is R plus in our simulation data, which is 6. So in type 1 noise, you can see as N grows, our method, which is black line, the percentage of the correctly estimated rank, it will converge to 100% as N grows. But compare under the white noise model, compared to the previous method, because they already have a deterministic form, and our method is just an estimation of the deterministic functions. So our method is still kind of worse than them in the sense of apply on the noisy white noise only data. But you can see in type 2 noise, the color and dependent noise, our method has a very correct, like a 100, when N grows, it converges to 100% of the rank estimation. But here, using a white noise model or even in screenshot, they have a very low percentage of the rank estimation. And this is just the estimator of the optimal shrinker. You can see even both in, the error rate of the eta, original optimal shrinker, and our estimator of the eta, which is het eta. So this is the error rate. Even in white noise and color noise, color and dependent noise, we have error rate is very low. The thick black line is a first is a D1 to D3 equal to 4. And the dash line, they are the weaker signals for D4 to D6. So both in the strong signal and in weak signal, our method in color noise, they have an error rate which is small compared to the white noise model or using a screenshot. So now we have the simulation that compared to our original motivation. How do we apply this method for the ECG data? So we construct this signal matrix. Then we apply the optimal shrinkage, our extended optimal shrinkage on this matrix. Then we will get the low rank data of the mother's part and this part for the fetal ECG and the background noise. And there are a red line here and a black line here, where the red line is using the optimal shrinkage of the white noise. And the black line is using our model, our extended optimal shrinkage. So you can see originally here, they are in the middle, they are the remaining part of the mother signal. You can see using the white noise, they are, because the morphology is not totally recovered. So there are some remaining parts of the mother signal here. Yeah. So it can, and our method doesn't have this error. And so our method has a better recovery of the mother ECG, and it will result in a better estimation of the fetal ECG. And this is a distribution of this matrix that we draw out the distribution of a noise matrix which contain the fetal ECG and the background noise. And this is our estimator of the rank lambda of the bulk age. You can see our estimator is exactly at the edge of the noisy only data. So it just prove that it just numerically show that our method to apply for the ECG, for this kind of model for ECG data analysis. And our rank estimator, our bulk estimator can be correctly estimated. And then we can decide how many data, how many singular values, what's the rank of the singular of the matrix. And this is applied to our algorithm to the CINC 2013, which is open source data for the fetal ECG database. So again, this straight line is like the mother's part with the fetus part is a real data signal. So the top figure is a reconstruction using a white noise for optimal shrinkage. And the bottom figure is using our method. You can see the amplitude of the fetus. We have a better recovery of the fetus using our method. And then we also calculate like accurately, how do we accurately estimate the location of the fetus using our algorithm and using the TREAD. TREAD means the traditional method using the optimal shrinkage based on the white noise. Also, we use the screen knot to have a reconstruction of the fetal ECG. And we compare how is it correctly we can locate after the optimal shrinkage and get the signals, and we detect the location of the fetal's peak compared to the manually annotated fetal ECG location by the clinical doctors. So you can see using our method, we have most highest rate of the accuracies here. And it has a statistical importance compared to the traditional method or the screen knot. This is only using when we have only one signals. And we also applied on the two signal. And how do we do it is more complicated in our paper. I won't explain right now. But if we have the data of two channels, then we have a higher accuracy, and it has also have a statistically importance compared to the using the white traditional method and compared to using the screen knot. And the NAE is how differently the location compared to the true location. Like if we the annotation is here, if we estimate it like around here, then the time interval will be large, right? So the smaller the value, the better. Right? So our estimation, we have a lower MAE compared to the other two methods. And we also apply on the arrhythmia database, because in CINC 2013, the fetus, they are just normal, they are healthy. And remember, we want to apply to recover the arrhythmia database, the arrhythmia case. We also cooperate with the doctors in Duke University, and we published the paper in 2019 that we want to see if we can also recover the arrhythmia case. This is the recovery of the arrhythmia called premature atrial contraction. That you can see here, the P wave, the amplitude are different, right? Here there's a bigger amplitude, here's a smaller P wave amplitude. And there are difference, the time interval between each beat, they can be irregular. So we want to see if we can recover the P wave better. And if we can recover the P wave even in arrhythmia database, we show that our method can have some recovery of the morphology for the arrhythmia database. And this data can be presented to the clinical doctor to see they have a correct diagnosis. So we have more cooperation with the school in Italy, University of Study the Cagliari, that we cooperate with Julia and Professor Daniel, that we have the real data from the hospital, and we want to see if we can have a better recovery with the arrhythmia database, and if we have a successfully contribution to the clinical medicine. And there are future works because you remember we assume that our noisy data matrix is just simply A times B times X times B. So what if we have a more complicated noise model? Like this model, it can be applied to like a fetal ECG data, but if we have a more complicated model for a signal and for noise, so how do we perform optimal shrinkage to different kind of data and to different kind of data of the matrix? Also, we already assume that we only have one heart. So, but if we only have one children, but what's the situation if we want to study, like we have a twin brother, twin sister? Also, is this our decomposition method is really the best? We want to design maybe better decomposition strategies. And how do we apply our algorithm to a real clinic hardware and or software application to clinical use? So this is a future world, and we try to move on. And that's my talk. Thank you for your notation. Thank you.
Okay, thank you, Pei-Chun, for a very nice talk. See if there are any questions. And for those on Zoom, you can just type questions into the Q&A box or into the chat. I have a few questions. So actually, this is maybe kind of a detail, but when you select the different clips, you select them, as I understood it, based on the peaks in the mother's heartbeat.
Yeah.
But there's no guarantee, right, that they're all going to be the same length. So how do you stack them into a matrix if they're different lengths?
Yes. So sometimes we have this bit. So we select the longest bit, longest duration. Then we crop each out, like each one is depending by the longest duration in this signal. For example, this interval might be the biggest interval in this signal, right? So we take this interval, and the left hand we divide it by divide by half. So the left hand, we have left window and right window, and if we apply this window to another heart rate, then there might be some overlap between here. So the matrix at the borderline, there might be some overlap, but when we do the denoise, and we can using some spline method to overcome this overlap and concat this signal together.
I see. But if there's overlap, that changes the noise statistics, right? Because you have multiple copies of the exact same observation.
Yeah. So this is one limitation that we sometimes might have the overlap. Yeah.
Okay. Okay. Yeah, that makes sense. So, so the goal here is to recover the fetal heartbeat, but you said that there could also be background noise, like in addition to the fetal heartbeat.
Oh yeah.
And I would imagine that would be especially true. You were saying people could use these tests at home and so on, where you don't have sort of very clean experimental conditions. So is there, like, how do you know that you're actually getting the fetal heartbeat as opposed to the fetal heartbeat plus a bunch of other stuff?
Yeah, so this is a part I didn't mention. Like right here, we can recover the mother's part very well, right? And then this is the fetus plus the background noise. So
do another shrinkage on top of
yes, we do a irritation. We do another shrinkage. That, for example, here in this signal, it's still noisy. Then, but right now we don't have the mother's part, so we can use another turn, another run to detect the fetal's heart peak location. And right now, because we don't have the big amplitude from the mother, so that location should be more accurate. Then we have the location, then we do an optimal shrinkage again. So that's why this accuracy of the F1 accuracy is important. If we have a higher accuracy, then we have a better recovery of the signal.
I see. It doesn't look like the e-op shrink is that different in performance from screen-out.
Yeah, because I think the problem is that because screen-out they cut off the some, they only select the top, the single values. They only have the top single values.
Yeah.
So the accuracy is depending by the peak, right? Which is the largest part of the signal.
Yeah.
So the location is decided by the peak. So in the sense of the detection of the accuracy of the location, it might have not so much difference. But remember, in our we try to recover the morphology P and T here, right? So if we only take the top singular value using the screen-out, the morphology might be different. So we need to apply the optimal shrinkage. And then we have another, using a simulation result to show that, I mentioned, using a simulation, which I don't show here, that we really have a better recovery of the morphology by simply using a background truth and to minus the recovery part with respect to the L2 known. In that sense, in our simulation, we do have a smaller error rate with the morphology recovery.
I see.
Yeah.
So you're doing a better job denoising, basically.
Yes.
But the results you were showing just now depend really just on the dominant singular value. So they're about the same whether you use screen-out or this other method. And
I have another paper which mentioned that how correctly, because here is some small wave, and we also want to locate the morphology and locate the location of the small waves, like these P waves. So I have another publication shows that how correctly we locate these small waves. But in that paper, I only use the original traditional method, but I haven't compared the screen-out and the optimal shrinkage. And I believe using our current method, we should have a better recovery.
I see. I have more questions, but we should probably wrap this up.
Sure.
So if there are no more questions from Zoom, then we can thank the speaker again and conclude. So thank you.
Thank you for listening. Yes.